Okay, this is chapter 24, fluid, electrolyte, and acid-base balance. And we're going to go ahead and get started now in here. Take a look at the learning outcomes. Basically though, fluids constitute a large percentage of total body composition, over half, 50 to 60%. And it is made up of minerals. You have dissolved minerals and organic substances that form ions called electrolytes. And this is an important concept about the electrolytes because that is going to play a major role in things that the body does. Remember, electrolytes are substances with a charge, either positive or negative charge. The body is divided into fluid compartments, primarily intracellular fluid, or ICF, and extracellular fluid, or ECF. The intracellular fluid is just that. It's all the fluid inside the cells. And the content varies depending on what type of cell, what type of tissue type, whether it's muscle or fat. The extracellular fluid is interstitial fluid volume, meaning the fluid just between the cells, in addition to what's within the blood vessels. The volume of blood makes up a part of the extracellular fluid component. And women have less blood volume than men. So if you take a look at this chart, you see you have total body composition of the adult male. Water is about 60%. Intracellular fluid 33% compared to 27% in the female. Interstitial fluid about 18%, female, male 21.5%. Note though that the plasma is the same. Plasma 4.5% male, 4.5% female. Solids in the male are about 40% and in the female about 50%. Now your body very carefully balances the fluid within it, and the water content stays stable over a period of time. So while there may be a little bit of plus here, a little minus there, over time your body keeps the water content, or wants to keep the water content, quite stable. So the way the body gains fluid primarily is absorption along the digestive tract. As nutrients and ions are absorbed, an osmotic gradient is created, which causes passive absorption of water. The way your body loses water is mainly through urination, over 50%. But there are other routes as well. For instance, digestive secretions are reabsorbed similarly to ingested fluids, so those secretions aren't lost except in abnormal conditions like vomiting or diarrhea. This chart kind of breaks down the amount of water that you take in various mechanisms that you take in as well as what you put out, but notice that at the end the net gain and net loss is the same. Here it is in a little different format where these fluid losses and gains occur throughout the body. So ICF and ECF compartments, they have a balance. They have different composition, and they're at an osmotic equilibrium. What does all that mean? That means that what that means is that when water is lost from the extracellular fluid for whatever reason, it is replaced by water from within the cells. And this is called the fluid shift. It occurs in minutes to hours and is to restore osmotic equilibrium. The state of dehydration results in a long-term transfer that cannot replace the ECF water loss. If you are so dehydrated, you've lost so much fluid from the ECF that the ICF fluid cannot replace it. The homeostatic mechanisms to increase the extracellular fluid volume will then be employed. So here's your intracellular fluid volume, plasma membrane. This represents a cell. This is the extracellular fluid. You have water vapor lost in respiration and evaporation from moist surfaces, a little bit of water lost in the feces, a little bit of water secreted by the sweat glands, most of the water lost in urine. Some water is absorbed from the digestive system. But when this level in the ECF drops below a certain level, then fluid from the ICF is going to move across the plasma membrane into the ECF. Looked at again on this page, you see that in the top one there is a balance. ECF, ICF, they're in balance. The two solutions are isotonic. In the second square you have an ECF water loss that reduces the volume and makes this solution hypertonic. Same amount of solutes. If you were to count each one of these dots, which represents a solute, okay, that's the same here as it is here, only you have less volume here, so it's more concentrated. So that concentration is going to create a gradient resulting in an osmotic water shift from the ICF into the ECF. So it will restore the osmotic equilibrium, but it will reduce the ICF volume as well. So routes of fluid loss from the body, you have sweat, you have feces, respiration, urination is the greatest. Your body also wants to maintain balance between minerals, and there's an equilibrium between the ion absorption and ion excretion. Your body controls these very precisely. There is major ion absorption in the gastrointestinal system and major ion excretion by the kidneys. Your sweat glands will excrete ions and water to a variable amount, but it is mostly excreted via the kidneys. Your skeleton maintains some ion reserves. The electrolyte maintenance is done by various mechanisms, and this chart shows you those mechanisms, whether it's active transport, channel-mediated diffusion, carrier-mediated transport, depending on the electrolyte. Now this is an important chart. That's the function of key minerals and the primary routes of their excretion. Sodium is one that your body uses a lot. As you remember from our talk about nerve conduction, the way muscles work, the sodium at the motor end plate. Okay, sodium is a major neurotransmitter. Next is potassium, then chloride, calcium, phosphorus, magnesium, and their function is here in the second column. And then the trace minerals are listed here: iron, zinc, copper, manganese, cobalt. So I said sodium was very important. ion, and it is. And so we're going to take a look at that in a little bit more detail here. Sodium balance is when the gains equal the losses. Relatively small changes in sodium are accommodated by changes in the ECF volume. The homeostatic response involves two parts: ADH, control of water loss and retention by the kidneys and by the thirst mechanism, which is located in the hypothalamus, and by fluid exchange between the ECF and the ICF. So when your body is in homeostasis, you have normal sodium concentration in the ECF. That homeostasis gets disturbed. You have increased sodium levels in the ECF. That's from, say, consuming large amounts of salt without adequate fluid, or something like that. That disturbance in the homeostasis stimulates the osmoreceptors in the hypothalamus. That causes secretion of ADH. And ADH, as you recall, is anti-diuretic hormone, which means that tells the body not to diurese, to retain the fluid, also stimulating thirst, promoting additional water consumption. Then it goes to recall of fluids. Because the ECF osmolarity increases, water is going to shift out of the intracellular fluid compartment, increasing the ECF volume, thus lowering the ECF sodium concentrations. Same amount of sodium, but you increase the volume, that lowers the concentration. This restores the sodium homeostasis. This chart shows the opposite. If you have a decrease in sodium, what happens? Well, again, the hypothalamus is inhibited at the osmoreceptors. ADH secretion will decrease. So by decreasing ADH secretion, decreasing the amount of anti-diuretic hormone, your body is now going to diurese more, or lose water through urination. And that water loss will reduce the ECF volume, which concentrates the ions, which is going to increase sodium levels in the extracellular fluid, and that restores homeostasis. When these changes in sodium occur, they're also accommodated by changes in blood pressure and volume. So the word we use for low sodium is hyponatremia. That's when you have a low ECF sodium concentration of less than 136 milliequivalents per liter. Remember, ECF, extracellular fluid, includes the fluid in the blood vessel. So if you were to take a do a blood draw, measure the sodium in it, that's going to give you that measurement of milliequivalents per liter. And this can occur from overhydration, drinking too much fluid, or inadequate salt intake. You get hyponatremia. The opposite is hypernatremia, where you have a high extracellular fluid sodium concentration, greater than 145 milliequivalents per liter. And this is commonly from dehydration. So increased blood volume and pressure results in natriuretic peptides being released. Natriuretic, to urese sodium, is what that means. You get an increased sodium and water loss in the urine. You get reduced thirst. You get inhibition of ADH, or less ADH being released. You have less aldosterone, epinephrine, and norepinephrine release. All these things occur as a result of the natriuretic peptides being released. Now, if you have a decreased blood volume and pressure, you get an endocrine response, which is going to increase ADH, increase antidiuretic hormone, increase aldosterone release, increase in the RAAS mechanism, or RAS, renin-angiotensin-aldosterone secretion mechanism. And these result in body responses opposite to that of the above. So let's look at this chart. You have beginning here, homeostasis, normal ECF volume. That homeostasis gets disturbed by a rising ECF volume that increases blood volume, which will increase distension in the atria of the heart, results in natriuretic peptides being released by the cardiac muscle cells. That increased natriuretic peptide will result in increased sodium loss in the urine, increased water loss in the urine, reduced thirst, inhibition of ADH, aldosterone, epinephrine, and norepinephrine. That results in reduced blood volume and reduced blood pressure, which is going to restore the homeostasis. Now, in this chart, you have normal ECF volume. You get a falling ECF volume by fluid loss or fluid and sodium loss. Perhaps you have trauma, and so you have a lot of bleeding, which is going to reduce your ECF volume. You get a decreased blood volume, blood pressure. The endocrine response is the RAS system, increased renin secretion, which will result in increased angiotensin II activation, increase aldosterone release, increase ADH release. The combined effects of those are to increase urinary sodium retention, decrease urinary water loss, increase thirst, increase water intake, creating a rising ECF volume, restoring homeostasis. So consider these questions, and based on what we've talked about up to this point, see if you can answer them. Potassium imbalance. Okay, the major gain of potassium is through the digestive tract. Major loss is through the kidneys. Primary ECF potassium regulation is by the kidneys, since the intake is fairly constant. It is controlled by aldosterone, which is regulating the sodium-potassium exchange pumps, which are located in the distal convoluted tubule and collecting duct of the nephron. In the case of low ECF pH, in other words, an acidotic state, then in order to get rid of those hydrogen ions which are contributing to the acidosis, the hydrogen can be substituted for potassium. Okay, so if the body is getting rid of hydrogen instead of potassium in order to reduce acidosis, that can result in an elevated serum potassium. Potassium is highest in the intracellular fluid because of that sodium-potassium ATPase exchange pump. So normally intracellular fluid potassium is about 135 milliequivalents per liter. But in the extracellular fluid, and again remember that includes the blood volume, it is at about 5 milliequivalents per liter. So take a look at this page, factors controlling potassium balance. you take in about 100 milliequivalents of potassium absorbed by the GI tract each day. About 98% of that is in the ICF rather than the ECF. The potassium concentration in the ECF is relatively low. Most of it's in this intracellular. So the rate of potassium entry from the ICF is through leak channels, and it's balanced by the rate of potassium recovery by the exchange pump. When the potassium balance exists, or it's imbalanced, then the rate of urinary potassium excretion matches the rate of digestive tract absorption. So your renal potassium losses are about 100 milliequivalents per day, which is the same as your average amount of potassium taken in by the GI tract. Alright, so this is the end of part 1. Please click part 2 for continuation.